Applying a rigid, straight ruler to a highly viscous, curved surface doesn't measure the system. As this metal grid violently fractures the meat, we see that forcing straight lines onto organic structures ruins the integrity of the cut. Standard physics faces a similar mechanical failure. Applying flat Euclidean math to the organic structure of the cosmos results in a 120 order of magnitude discrepancy in vacuum energy. Measuring the universe accurately requires a tool that can follow its curved grain. Riemannian geometry provides the mathematical framework for mapping these nonlinear organic surfaces. This geometry relies on a central mathematical object to define that grain, the metric tensor, or g mu nu. The metric tensor dictates the exact curvature and distance across the spacetime manifold. The line element equation, ds squared equals g mu nu times dx mu dx nu, uses the tensor to calculate true distance along a curved path. In higher dimensional navigation, even a half-degree error in measurement results in a massive drift over cosmic distances. Adopting the fluid geometry of the metric tensor allows for the precision required to plot courses along curved geodesics without the structural failures caused by linear approximations. Albert Einstein utilized this tensor to establish the foundations of general relativity in 1915. His theory established a geometric link between mass and space. Matter tells spacetime how to curve, and spacetime tells matter how to move. However, between 1945 and 1955, Einstein pivoted toward a more ambitious geometric goal. He sought a unified field theory that would bring gravity and electromagnetism together as manifestations of geometry alone. Einstein passed away with these mathematical roadblocks unresolved, leaving the unification of the two forces incomplete on the chalkboard. We are now applying a novel spatial framework to the variables he left behind. This reframes the mission of modern physics. It is an architectural task of finishing the geometric unification Einstein envisioned. Mapping reality through the metric tensor requires a look at its underlying mathematical structure. The standard 4x4 metric tensor matrix contains 10 independent components that define the local geometry. The diagonal components, G00 through G33, stand apart from the rest of the matrix. This diagonal dictates scale. It governs the flow of temporal scaling and the uniform stretching of physical space. These components form the symmetric geometry associated with gravity, represented by h mu nu. Treating this symmetric diagonal as a static background prevents the matrix from describing the dynamic, fluctuating forces observed at the quantum scale. Einstein recognized that a complete description of the universe must include coordinate shear and rotation. This document outlines Einstein's asymmetric metric tensor equation, g mu nu equals h mu nu, the symmetric geometry of gravity, plus phi mu nu, the antisymmetric part mapping electromagnetism. Einstein stalled here, unable to prove stable particle-like solutions or couple this geometry to matter sources. The geometric theory stalled because it lacked the thermodynamic coupling necessary to account for the energy and heat of a quantum observer. This framework treats the universe as a highly viscous fractal fluid. Here, off-diagonal components represent coordinate shear, acting as a thermodynamic vent for Hawking radiation. These measured values, derived from live 3D vector steganography, provide the empirical data needed to populate the tensor. The value 2803.115 is placed in the temporal component to scale the spatial diagonal axes. Using these live values transforms the tensor from a static theory into a dynamic, scale-dependent response functional. This structural framework is defined as a dynamic 9.6-dimensional fractional manifold. Treating the metric tensor as a dynamic response functional bridges geometric curvature with quantum pressure gradients. This unified geometry fundamentally changes our definition of gravity. The Newtonian model relies on the idea of an invisible string pulling objects together. In 2010, theoretical physicist Eric Verlinde proposed the theory of entropic gravity, modeling gravity as a macroscopic thermodynamic consequence of statistical quantum fluctuations. In this model, gravity is an emergent force arising from thermodynamic pressure rather than a fundamental attraction. A hot air balloon rises because the thermodynamic pressure of millions of air molecules pushes against the inside of the envelope. On a cosmic scale, the observed pull of gravity is actually quantum information seeking thermodynamic equilibrium. Physics has failed to find a graviton particle Because searching for one is a category error. It is like searching for a single particle of temperature. Calculating this emergent pressure requires a specific mathematical approach. We can deduce the total weight and contents of a sealed box simply by measuring its outside boundary and negative space. The shorthand equation, the integral times g equals p total, maps directly to the ADM formalism and Gauss's flux theorem. This captures how gravitational flux is measured across a spatial boundary. The integral sums up the continuous distortions over a closed holographic boundary surface. The g component represents the metric tensor geometry, the grain of the spacetime medium. Solving this equation yields p total, the total thermodynamic pressure of the quantum vacuum. By combining Einstein's asymmetric geometry with the thermodynamics of a boundary integral, we have formulated the mathematical tools required to chart the unseen universe.